Okay, so now that we've gotten through all of Newton's three laws, I want to discuss all of them together because I want you to be able to understand conceptually what they really say and how they relate to the motion that you see in your everyday life. So, just to recap all of the laws, remember that the first law is called the law of inertia because an object that is in motion tends to stay in motion, an object that is at rest tends to remain at rest. That's a very commonly known law. That's Newton's first law. Now, it doesn't mean we can't change the motion of the object. It just means that's what tends to happen. That's the natural state of all objects is to be in motion, and it's called equilibrium, to be in motion without acceleration. The second law deals with acceleration. We can accelerate or change the motion of an object, and it takes a non-zero net force. That's what causes acceleration. Newton's second law had an equation. That equation is sigma F equals ma. Newton's second law also told us that there are two things that influence the acceleration of an object, and that is the net force acting on that object and its mass. Net force was obvious. The greater the force, the greater the acceleration. That's a direct relationship. The mass is an inverse relationship. The greater the mass, like this elephant, the smaller its acceleration. That was our mouse elephant thing we talked about. The mouse has less mass, therefore it will experience greater acceleration with the same force. So the first and second law were the only two laws that talked about one single object, whereas the third law, now we're talking about two objects. We're talking about equal and opposite forces that two objects exert on one another, and these are called Newton's third law pairs. And that happens anytime two objects are in contact with one another or interacting. So now that we know what Newton's three laws are, and we've talked about those, I want you to be able to identify from reading a scenario to be able to identify which of Newton's laws explains a motion in that particular scenario. So again, first law, object in motion stays in motion, object in rest remains at rest. And so that means in any scenario where something was previously in motion and continues to stay in motion, we're going to identify that as Newton's first law because that's what's causing that phenomenon. For instance, you're slamming on the brakes, your body flies forward, kind of like this example here. If you've ever watched The Office, you remember this episode where Jim is driving, Dwight is in the back seat, Dwight buckles up, Jim slams on the brakes, and Dwight hits his head on the headrest because an object in motion tends to remain in motion. Or we could talk about another example. Anything that was previously at rest and tends to remain at rest, even though it doesn't look like it should. That's also Newton's first law because of inertia, like this tablecloth trick. Let's look at what this is about.
Use the property of inertia to pull off this trick without breaking a single plate.
So in this example, the tablecloth moves and all of the plates and cups and forks, everything stays where it is because of Newton's first law that says an object that is at rest tends to want to stay at rest. Any example, any scenario that looks like these, we're going to call that a Newton's first law scenario. The thing that's happening in that scenario is related to Newton's first law. The second law, where acceleration is determined by net force and by mass. So any scenario where a bigger force produces bigger acceleration or a smaller force produces smaller acceleration, we're going to call that Newton's second law. For instance, swinging a baseball bat harder makes the ball go farther, right? So if you want to hit a home run, you got to swing harder. That's applying a larger net force to that object. That's Newton's second law. Net force increases, acceleration increases. We can also think about scenarios where an object is experiencing smaller acceleration because of its greater mass or vice versa. So this is the second thing that affects acceleration according to Newton's second law. The first thing was the force applied to it. The second thing is its mass. Greater mass, less acceleration. Smaller mass, greater acceleration. So for instance, you can throw a small baseball, a 0.15 kilogram baseball, way farther than you can a 7 kilogram shot put. If you apply the same force to both of these objects, they're going to experience different acceleration. Not because we applied a different force, but because Newton's second law says that mass is inversely related to the acceleration. We can also look at a bat hitting a baseball, and we've already talked about this before when we talked about Newton's second law. Even though we know that the bat and the ball exert equal forces on each other according to Newton's third law, even though the force is the same exerted on each of those, they each have a difference in acceleration due to their difference in mass. The smaller ball is going to have a much greater acceleration because it has less mass. The baseball bat has a much smaller acceleration because it has a larger mass. So that's Newton's second law. The third law was where we talked about two objects exerting equal forces on each other in opposite directions. So it's really important that when we read these scenarios, we have to note that any two objects are interacting and they're exerting equal forces on each other. That's like the only thing, that's the only condition that has to be met to be Newton's third law. But it's got to be forces they exert on each other. That the forces must be the same. So for instance, you sitting in a chair, you exert a force on a chair, the chair exerts a force on you. That scenario is due to Newton's third law. Two people pushing on each other, right? If two people are pushing on each other, as you see here in this scenario, as in maybe they're two football players, no matter what their sizes are, no matter what the acceleration is, Newton's third law says they must exert equal forces on each other. Now, they might not experience equal acceleration because the one with the smaller mass gets the greater acceleration, but their forces exerted are the same. Again, we talked about this one already, the bat hitting a baseball. If you have a scenario that says which of Newton's laws explains that the forces they exert on each other are the same, we're going to call that the third law. If you have a scenario about a bat and a baseball and it talks about the difference in acceleration, go back here. Difference in acceleration is Newton's second law. The second law talks about differences in acceleration due to net force difference and mass difference. But the third law specifically says that that bat and that baseball must exert equal forces on each other. So if the scenario you're reading deals with the equal forces of those two objects, that's going to be the third law.